we have only 2 more stages to do. So the next stage is write back. And write back is when we take results and we write them into the register file. So clearly we need the register file. We've already seen that we're going to take the value from memory and feed it into the val-m port. Similarly, we're going to take the value out of the ALU, that val-e signal, and we're going to route that into a separate write port called the E port, or execute. And then don't forget those pesky little conditional moves. We're going to need our conditional logic to decide when we should move conditional move results into the register file. So let's look at some wiring. Just like we had the M port before, we're going to introduce an E port. And the value that we'll write into the E port is going to come from val-e. The question is, to what register should we write? And normally, it's just going to come from RB. But depending on the opcode, we may or may not want to actually write things. Recall, we use the ALU to produce things in val-e that don't necessarily get written into the register file. So in the normal case, where we do want to write into register RB, we're going to tell dest-d that that's the register where we want to write things. And we're going to give it the opcode to decide when to do that. But now we have to deal with those pesky little conditional move operations. So we're going to take the condition code and we're also going to wire that into dest-d. So the logic for dest-d is normally going to say, just take whatever was in RB, and if the condition says you should move it in, move it in. But every once in a while, if the instruction is something like a push or a pop, it might say, rather than taking RB, we're going to use the stack pointer and update that. So for things like push pop, call return, dest-d is going to be responsible for figuring that out. Our last stage is PC update. So we've done everything we need to do for an instruction, and now we need to figure out the address of the next instruction. So we're going to use the program counter, but we're also going to use val-p, which is what we think we're usually going to execute next. But sometimes, like in return, we're going to get an address from memory. Sometimes, basically call and jump, the address might be in the instruction, and we have to deal with those pesky condition codes. So let's add a new piece of logic here, which is the PC update logic, or we'll call it next PC. And if you recall, I promised you that we would figure out how to get that return address from memory into the PC. So we're going to take val-m, and that's going to be one of the inputs to this next PC. The other input is going to be val-p, because when we just execute sequential code, that's normally where it comes from. And then to decide what we're going to do, we need to route the output of the condition code in here, because if we have a conditional jump, that's going to determine where we go. And we're also going to need val-c, because in jump instructions, we get the signal, or the address are those 8-byte quad words, and that comes from val-c. So we feed val-c, val-m, val-p, and the condition code. And based on those, we're going to figure out what the next value of the program counter is. And on that note, you now know how to implement the y86. I'm going to guess that you might not have this all committed to memory. And even better, I'm going to tell you you shouldn't commit it to memory. Instead, what I hope you'll take away is sort of a thought process that you can go through to figure out where signals need to be and how we get them there and when we get them there. And the kinds of questions that we might ask you, and we'll give you time to practice this, is imagine we were going to implement a new instruction. How would we change this wiring diagram to facilitate that? So don't spend time memorizing this diagram specifically, because this is carefully constructed to fit on a slide. Instead, think about how it was that we decided where we needed to route all the signals.